All right, let's just get right into it. If you've been on the internet at all lately, you've seen them. These wild videos of robots folding laundry, dancing with this crazy agility, or cleaning up a messy room. And the leap forward, it feels so sudden, right? Like science fiction just became reality overnight. But the reason for this explosion in what robots can do isn't just about better motors or gears. Nope, it's something much, much deeper happening behind the scenes. For decades, the robot in our heads was that big, clumsy arm in a factory, bolted to the floor, doing the exact same thing over and over, millions of times. Super useful for sure, but it was stuck in this perfectly structured, predictable world. But now we're seeing robots operate in the absolute chaos of the real world. They've got these fluid, adaptive movements, and they're handling things as unpredictable as a shirt fresh out of the dryer. So, that's the big question here. What is the fundamental difference between the robot that was struggling just to open a door a few years back and the ones we're seeing today? What actually unlocked this whole new world of physical skill? The easy answer is AI, but that's not specific enough. It's a very particular kind of AI. See, we've gotten used to AI that can see the world and talk to us about it. This new wave, though, this is about an AI that can actually act within it. It can do things. So, most of us have played with vision language models, or VLMs. You show an AI a picture and ask it a question. It takes in images and text, churns it through a massive model, and spits out text. It sees, it gets it, and it talks. Simple enough. Okay, so how do you make the jump from just talking about something to actually doing it? Well, researchers evolved the VLM into what's called a VLA, a vision language action model. And the big innovation is in the inputs and the outputs. It doesn't just see the world. It also takes in the robot's own state, like where are my joints right now? And then, and this is the crucial part, instead of outputting words, it outputs the direct actions needed to control the robot. So, that's it. Problem solved, right? Just tweak a VLM and you've got a robot brain. Well, not quite. This is where we slam into the real fundamental challenge that the entire robotics industry is facing. Think about where these models learn from. The difference is just massive. A VLM has the perfect teacher, the entire internet. Billions of images, trillions of words, a practically infinite library of data to learn from. But a VLA, it means data about physical stuff. How to pick up a cup, how to fold a towel. Where in the world do you get petabytes of that kind of data? You can't just scrape it off the web. And this isn't some small hurdle. The researchers at Physical Intelligence, whose work we're digging into here, they literally call this the trillion-dollar question for the industry. Figuring out this data problem, that's the key that unlocks everything else. So what do you do if the data you need just doesn't exist? You have to create it. And that's exactly what this team did. They built what they call a data engine, a system designed from the ground up with just one goal: to generate a massive, high-quality dataset of physical robot actions. Here's how it works, and it's actually pretty brilliant. First, you have human experts use this special rig with leader arms to remotely control a robot, basically showing it how to do a task perfectly. Then, every single successful movement, every joint rotation, every grasp is recorded. This huge stream of top-notch data is then fed into the vision language action model. And after all that training, the model, which they now call a policy, can be deployed, and boom, the robot can do that complicated task all by itself. And the scale we're talking about here is just wild. Before this project, the biggest public dataset of this type was around 3,800 hours. Within their first 6 months, their data engine collected 10,000 hours of successful demonstrations. But here's the real kicker, the key insight. It's not just about how much data you have. It's about how diverse it is. They started in sterile labs, sure, but they quickly scaled up to hundreds of different tasks. And then, and this is the game changer, they put the robots on wheels, collecting data from mobile robots doing things in hundreds of unique, real-world homes and offices. So why does all that matter? Why go through all the trouble of collecting so much varied data? Because this mountain of diverse experience is what unlocks the holy grail of robotics. And that holy grail has a name: generalization. This is the big one. It's the ability for a robot to walk into a kitchen it has never, ever seen before, with a totally new layout, and still figure out how to do something complicated like make a cup of coffee. That's the difference between a pre-programmed machine and a truly intelligent agent. So to prove this, they ran this really clever experiment. They trained different AI models on data from a handful of homes, or 10 homes, or 50 homes. Then they tested all of them in a brand new house the AI had never seen. The results were crystal clear. The more diverse homes the robot trained in, the better it did in a completely new one. It wasn't just learning one kitchen, it was learning the idea of kitchen.
And this leads to a conclusion that is honestly kind of mind-blowing. With enough diverse data, the model's performance in a totally new home eventually got just as good as, and sometimes even better than, a model that was trained only in that specific home. Let that sink in. That is an absolutely groundbreaking discovery. It proves that diverse data is the secret sauce for a general-purpose robot.
So what does this unlock? Some incredible, almost futuristic skills. These models can now take a super high-level command, like clean the bedroom, and just figure it out. They'll automatically break it down into smaller steps. Pick up the trash, put the pillow on the bed, straighten the blanket. They can keep at these plans for up to 10 minutes straight. And get this, in one demo, their AI model was able to successfully control a robot body it had never physically met before. And this brings us to the final critical takeaway. For years, we all kind of assumed the biggest roadblocks in robotics were hardware problems. Better hands, better sensors. But this research points to something else entirely. The main bottleneck isn't the physical body anymore. It's the software. It's the AI model, the intelligence driving it. The hardware is getting good enough. The brain is what's finally catching up. So there you have it. That's the secret behind this robot revolution. It's not just about better metal and wires. It's a new kind of AI, powered by a new kind of data, that has finally unlocked the ability to generalize in the real world. Which, of course, leaves us with one last question to chew on. If you had access to a single AI model that could skillfully operate any robot in the world, what would be the very first thing you'd ask it to do?